land on which the Fields Institute operates. For thousands of years, it's been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. And now I'll give it over to Zhenheng Wu, who's our principal investigator at the Mathematics for Public Health program, to introduce our speaker today.
Thank you, Ben. Can I ask anybody in the audience to tell me or send me a chat whether they can hear me or not? Probably not you, somebody from the audience. Okay, thank you very much. All right, good. So I'm Zhenheng Wu. Good day to everyone. And I'm very pleased to have a distinguished colleague, Linda, Professor Allen, with us today. And Linda does not need introduction to this community. She's a SIAM fellow since, she has been SIAM fellow since 2016. She's the speaker for the Kowalski Lecture at the International Congress of Industry Applied Mathematics in 1915, and Linda was awarded Home Professorship from Texas Tech University. Many of us have been strongly influenced by Linda's work, and in particular the classical book on stochastic process with application to biology. And Linda is particularly credited for her influence in training next generation of modelers, and she was the main speaker to the inaugural summer school series organized by my texting, and in the summer schools organized by CDM, Center for Disease Modeling, in subsequent years. So with that, Linda, I really want to thank you, and the voting is with you now, Linda.
Okay, thank you, Zhenheng. But let me mention that you were the one who was instrumental that got me involved in these summer programs, and it was just such a rewarding experience. So I thank you for that. So, yeah, I really, really enjoyed that. So I'm going to talk about modeling seasonal variability and how it affects disease outbreaks in zoonotic infectious diseases today. And so what I'd like to talk about are several things, but the goal is just to understand some of the effects of seasonality on the occurrence of disease outbreaks from using deterministic and stochastic modeling approaches. So I'm going to begin with a little background on zoonoses, seasonality, and what I mean by a disease outbreak. And then the major thing that I'd like to put across is to use a new method in branching processes that includes seasonality. So I'm going to spend some time on that, apply it to a dengue model that I did with a colleague of mine, where we used the seasonal mosquito dynamics, which in this case, it turns out, although the model may not be real complicated, and the seasonality is fairly simple too. Then go on to something that we've been considering recently is Lyme disease, which I know Zhenheng Wu and many others have been working on a lot. And so this is not finished work, but so comments on this would be greatly appreciated, and avian influenza a little bit. So we haven't gone as far as both of those. And then just acknowledge all of the collaborators that I've had fortunate to work with. So beginning with some background, the term zoonosis was actually first coined by Rudolf Virchow, who was a pioneer in cellular pathology, and he was working with pork, and notice this affection that people can get infection, the trichinosis from undercooked pork. But he coined this term zoonosis as an infectious disease that is passed between humans and animals, non-human animals generally, but it can go both ways. But we usually use it from animals to humans, and that's why I'm going to have it here. So it estimated that over 60% of human infectious diseases are zoonotic, and of those, 75% of them are emerging. And what we mean by emerging and re-emerging is just newly recognized or newly evolved, where the incidence has increased or the range has expanded, either host or vector. In the Centers for Disease Control in the United States, they list on their website 8 priority zoonoses. And I've just highlighted the 2 that I'm interested in a little bit here today, but there's many other ones. that they consider priority. And the priority is not because others are not important, but just because they're emerging and maybe we can do something to help. So zoonotic influenza or avian influenza, which is a virus spread from wild birds to domestic poultry, and then spills over to humans, and Lyme disease, a bacterial infection from deer tick that feeds on mice, deer, and other small mammals. And so those are the two, so they are very important. And the 3 infectious diseases that I'm going to mention here, they do have seasonal drivers. And for example, the first example that I'm going to give when I talk about these is dengue fever. The seasonal driver is mosquito population because it fluctuates and it's peak in the rainy season. Lyme disease, seasonal, the tick is the driver, but it has a very complex life cycle. But summer, when the nymph ticks are out, humans are infected. And the last one, avian influenza, wild ducks are the, in this model, it's going to be the wild ducks are the driver, where winter humans, both when they migrate down south, humans and poultry become infected. So these are the drivers. And I'll just mention there's 69 of them mentioned in this publication by Martinez that have seasonal drivers. Okay, so I'm just going to give a little bit of background before I go into the particular models for calculating disease outbreaks using the standard SIR stochastic model. This has been studied and well known for a long time. So, but just to give you a sense of what I'm interested in here and like to show you. So if we start with the ordinary differential equation for the SIR model, okay, here I have the I equation here. Beta is the transmission rate. I'm using the frequency dependent here. And so it looks like this. So basically there's 2 parameters that are important here, the beta and the gamma. And of course that determines the R naught in this case. So, but if we model this, what I'm going to do is model this using a Markov chain, continuous time Markov chain, where we can use the 2 events that occur in here. Either there's a transmission where a susceptible becomes infected, or a recovery where the infected individual recovers. Those 2 events can be considered a probability if we multiply this rate by a small time delta t. And so either you have a transmission with this probability here, I and S delta t, or you have a recovery and nothing else happens in those changes. So, okay. So my models are going to be related. So I'm going to use the framework of the ODE to formulate a continuous time Markov chain in this sense. Okay. But there's very, very important differences when we start when an outbreak occurs in the ODE and the CTMC models. Certainly the ODE has a unique solution if you know the initial condition, whereas the CTMC has many solutions referred to as sample paths or stochastic realizations. In this example here, there's a population size I assumed of 500. The N is 500. We start out with 1 infected individuals. The parameters are here such that gamma is 1/7, so about 7 days, it lasts 7 days. And then the reproduction number beta over gamma. In this case, it's 2. So beta in this case is 2/7. Okay, so R naught is 2. And so what I'm showing here is a simulation. The solution for the infected, you can see, goes up very high, up to close to, at one point, there's 80 infected here. And then I also simulate 3 sample paths here. And of course, you only see one of them, the red one. There's a red one, a green one, and a blue one. Because 2 of them, if you start out with such a small number of infected, those 2 happen to recover. Okay, so an outbreak occurs only 1 of these 3 here. And then I also show it for a case where I've reduced the R naught, so it's less than 1. And then, of course, we know that there's no outbreak here. And so this black line is the ODE solution. And these 3 different colors here represent 3 different sample paths. And of course, they look this jagged because we're changing 1 unit at a time, right? And 1 individual is at a time, so they're all integer valued. So it can, in this particular simulation, there were 3 cases, but then they all recovered. If I ran it again, I could go up to 8 cases or something, but generally it's not very many cases. Okay, and so as I said, this has been known for a long time. In Whittle in 1955, gave an approximation for the probability of outbreak by linearizing their rates, linearizing the rates by assuming that your population is at the disease-free equilibrium, right? At 500, and then you introduce one individual in there. And so the approximation for the probability of outbreak they found was 1 minus 1 over R naught I 0. So R naught is still a threshold in the stochastic formulation because we're using some of the assumptions from the ODE. It's still, so there's, but it doesn't, the probability of outbreak doesn't occur with probability 1. Okay, as it does in ODE. It's different from that. And so in this particular case, when R naught is 2, and you start out with 1 infected individual, you calculate it 1 minus 1 over R naught is 1 minus 1/2, so you have 1/2. So half of the time you'll get an outbreak and half the times you won't. Okay, so the one we actually realize, the ones we see are those that where you have an outbreak. Right, so that's some basic background. So now what we're going to do is we're going to include seasonal variations in that by including periodic coefficients. And what happens is that you result in a periodic probability of an outbreak. So how this is computed, and I'll show this in a little bit, but its probability of an outbreak can be computed from, we're linearizing near the disease-free state, and it can be attained from a branching process approximation. So in this example right here, I'm using very similar parameters to that last example where I used gamma's 1/7. Beta of t is 2/7 times this sinusoidal function here. Okay, but on average, the beta has a value of 2/7. And in fact, even for this periodic coefficient in the simple SIR model, the basic reproduction number is 2. Okay, so here I'm showing you on the left right here, this is the reproduction number as a function, instantaneous. Let me call it the instantaneous reproduction number, okay, which I put right here. This is how it's changing. And I put this threshold 1 to show you when this instantaneous one goes below the threshold of 1. Okay, so I said, well, so let's try just using Whittle's approximation with this instantaneous one. And so this is what you get, right? So I took and calculated this thing. And so you see this rise when it's when it's above 1, but when it gets below 1, of course it's negative, but that doesn't make sense. But I chopped it off at 0, right? So they're all below 1. So you see this little dip right here. So this is that. Now this figure right here on the far right is actually using branching process, using equations to find when you have a major outbreak. It looks very close to this thing right here, right? But there are some differences here, okay? And also, what are these little blue circles here? So what I did was this curve right here, this black curve here is found by solving a differential equation for the probability of, I solve a different equation for probability of extinction, and then I take 1 minus that for the probability of an outbreak. I'll show you in a little bit. And then, okay, so that's what I get for this black curve. But what are these little blue circles? What I did was ran the SIR stochastic model, the CTMC model. I ran it, I think it was 10,000 times until either the I hit 0 very quickly, or it reached a value of about, I think it was 40. And if you see the last figure, it goes up to the maximum of 80. So when it reached 40, I said, well, it's not a major outbreak. And then I plotted the proportion of times where it didn't reach that level. And you can see, if I started it at time equals 0, I reached very closely to this curve. I started at 90, the probability that was an outbreak is here. And then when I was down here, it's up here. And there are differences here. For example, look at 180, okay, where this is still quite large. You don't have a major outbreak. And also 270, where you've been at 1 a long time, but it's almost no outbreak. But shortly after there, you have differences in these things right here. But this kind of gives you, so it seems like this might be a good approximation, but we'll see that it can't be used, okay? Because this is a simple model, but it's gives you some idea. Okay, so I'm going to just give you some of the background that I'm going to use for the other models. We're using multi-type branching processes. This is when we have multiple stages to calculate the probability of outbreak, because there aren't simple formulas. So some of the assumptions behind this branching process theory that to make it work is that we have to have the susceptible populations are at a stable disease-free state. It also is, it's not assumptions, it's curves. The infected populations are unbounded because we are approximating this just like you do with the R naught, it's an exponential growth. So they become unbounded. Individuals infected at time t are independent of those infected prior to time t. But when we have a small number, we're assuming that there's no interaction here. This is the Markov property. So these are mathematical assumptions. So to compute the probability of a disease outbreak, we're at the disease-free state, and we use the backward Kolmogorov differential equations. So now we're looking at the probability. So we have many infectious states, not just one. So this boldface I is supposed to represent you have many infectious state here, and they all start there, then they end up at 0. So we start out with 1 in one of these stages, and this is representing the probability that we go from this one infected to all of them no one being infected. We're starting out at time t naught, we're going to time t. So we start at t naught and going to time t. So if we apply the Blackford-Kolmogorov differential equations, we can write equations for these, because we have all these simplifying assumptions, and it looks like this for each one of these stages, I1 through IN. And what this is that this is a probability generating function, assuming that if you start out with one infected in that stage, what happens to it. So we have this, but the interesting thing about this is different from the forward is there's a negative sign here, and this depends on the initial time, okay? So in order to solve this and get information about when they do this, what we have to do is we have to solve this as a function of t naught. So we have to do a little bit of changings here to this equation. And so this is what we do. We make a change of variable. We let f equal the difference between t and t naught. This is always, anyway, t minus t naught, okay? And then we define a new function as a variable of s. And you notice there was only, only a derivative with respect to t naught. So it turns out we're going to fix the time now. We're going to fix it at time t equals 0. And then we're going to let s go to infinity, t naught go to minus infinity. It turns out that this solution right here approaches a periodic solution. Why? Because the other ones are all, it's a simple system. We have periodic parameters. There's a common period t. It approaches a periodic solution. The probability of disease extinction, then, because I'm solving this backward, right? I'm going backwards in time. I have to flip things around. And so to get the probability of extinction, starting at time t naught and going to t, approaches this periodic function. And this is the estimate I use for probability of extinction, starting at time t naught with 1 infected in the jth stage. But if I want to calculate the probability of an outbreak, and we have many in different stages here, which I just call by this vector I, okay, you take 1 minus that. If you only have 1, it's just 1 minus that. If you only have 1 in stage j, it's just 1 minus that. But you may have 1 in stage, you have I1 in stage 1, you have IN in stage n. And the independence of these, when you start out with a small number of infected, make these probabilities, we're able to multiply them. So it's 1 minus the probability of these extinction probabilities that you calculate raised to that power. It's 1 minus that. But usually you only want to, I mean, once you've got a lot of infected, everything, this theory doesn't, it's when you're interested in this, when you have a small number of infected. Okay. So also interesting is the basic reproduction number is a threshold not only for the ODE, but it's also a threshold for the branching process. For the periodic functions, we have to use this, often you can't compute it analytically, but you have to use this other method, find the spectral radius of this fundamental matrix here. and then calculate the lambda such that lambda is equal to 1. Wang and Zhao in 2008 paper. So, but you can calculate this threshold, but it turns out the branching process threshold, it's the same. It's still the same. It turns out when it's less than or equal to, then the probability of outbreak is 0. But if it's greater than 1, the same R naught that you get from the ODE, the probability of outbreak is periodic with period T, and it lies between 0 and 1. Okay, so we have a periodic one. So the R naught that we calculate from the OD can be used in the branching process threshold, and we know that we should get a periodic probability of an outbreak. Okay, so now here I'm going to do it for an example. First example is I'm going to use dengue fever. This is a viral hemorrhagic disease. It's caused by a dengue virus. It's a flavivirus. But I mention this because in the priority zoonosis, although the dengue isn't, because it's not really a zoonosis, it's Zika and West Nile virus are also of this same family here. It also has a potential origin that comes from a sylvatic cycle in monkeys. So maybe this is one reason to say it's okay, I can talk about this as zoonosis. It's not really a zoonosis. It's transmitted to humans from the mosquitoes, either Aedes aegypti or Aedes albopictus. And there's also related viruses. If you get one, sometimes you get a more severe disease by getting the other one. I'm not going to talk about those. I'm going to look at one, just infection by one virus, because there is a strong seasonal patterns in rainfall and temperature that are directly linked to transmission and dengue fever. And so as motivation is this paper by McLennan, Smith, and Mercer, where they give the data from North Queensland, Australia. And what drives these cycles, they use the wet and the dry seasons. And this is data from 2000 to 2012. All it's indicating is the cases that have been reported from these years. And you can see that it is seasonal and very highly variable, right? Highly variable depending on the season. I mean, in some years it's very high. Here, so in the model, we're going to simplify this, the mosquito cycle. So we're not looking at all the, the eggs, the larvae, pupae, and adult. We're only looking at the adult stages because, and it has a 12-month cycle. 7 to 10 days from egg to adult during the rainy season, but eggs can survive up to 8 months in the dry season. So we're assuming that everything is driven by the mosquito cycle. So we're going to formulate ODE and CTMC models. And I'm just showing the diagram here. So the human population are with the subscript H, susceptible, exposed, infectious, and recovered. And the vectors of the mosquito are by the V subscripts here. And what's driving this is this recruitment rate here in this mosquito. The recruitment rate, which it can be birth or immigration, is a time-dependent one. And so I just put on the bottom the R naught that what you would get if you have constant parameters. But what if NV is, if this recruitment rate is time periodic, then the mosquito population is going to also be time periodics. Okay. And so so I'm using this, okay, so this, so I'm assuming some very simple periodic functions to check the theory and to see what the theory can tell us about these things. So here's the human population has 500 seasonal recruitment, and V of T drives the susceptible mosquito population. And so the mosquito population is represented by the capital N with the star here. And it's actually the blue here. So you can see it's very closely related to this because of the way it's formulated, but mosquitoes can go up to 2,000 and then down to close to 0 because the amplitude of this is so high. So we're assuming that this is a 12-month cycle, and then it repeats. And to see what we can see about how seasonal changes change the outbreak probabilities. Okay, So the probability of a disease outbreak can be estimated in different times during the year. Okay, so I'm just showing this, and I'm showing this is a sample pass of the exposed in the human and the exposed and infected in the human, exposed and infected in the mosquito population. Okay, so we were at a entirely susceptible population. The infection is introduced at time equals 6 months. The R0 we calculated in this model was with the parameter value is 1.54. And the probability, I'll show you in the next page, is about 80% or 0.8. So this I'm showing you, this is only one sample path. And you can see, so nothing happens because until it was introduced, I think it was one host and one infected mosquito are introduced in the CTMC. And you can see, because it's all mixing together here, you see this rise in the infected population. Okay, so you do have this is an outbreak, and mosquito population is even much higher. But you see, what happens what's interesting to me, so why I showed this, because at 6 months, what would you expect? Because mosquito population is decreasing, right? But you see a small outbreak, and it's still maintaining the population. So it's not until about 12 months, right? When it's on the rise again, that you actually get the big outbreak. But there is an outbreak here, right? So, okay, so now, okay. So think about this cycle here. Okay, oh, and so just to show you, in order to calculate for the branching process, you have to look at all the infected stages. And so there are these 4, right? And so for each one of them, you'll have an equation that you have to solve backwards, and then take the look at the periodic, find a periodic solution for this. And so you do it for each one of these stages. Okay, and then you solve it. And so the solution is going to depend on how many of each one of these that you introduce. Okay, so in that last example, I gave you one infected human and one infected mosquito are introduced at time equals 6 months. But now, here either introducing one infected human, one infected mosquito, or both. So now I'm showing the graphs that were generated by the assumption of having the recruitment rate periodic, like that sinusoidal cycle. And if you look at this, it looks very similar to the, this is the sinusoidal cycle, but you can't just predict it by looking at the R0, because there's only one R0 and you have different stages, right? So it's quite different when you introduce a mosquito, whether you introduce both of them or you introduce just the human. And so if you started at 6 months, right, here's the probability of an outbreak. Probability of an outbreak is very close to about actually, this is the one that I actually used here, very close to 0.8. Okay. And so, but if you introduced at 9 months, right, where it's very low, there's still a positive probability of outbreak, but it's much less, right? And the probability of an outbreak even extends much further beyond that sinusoidal function, right? So it can be very high, but it's only in a very small region right here. Even though the population dips below, even the threshold dips below 1, you still get positive probability of an outbreak. So it gives us some more information, and it's not, it depends on all the things that are happening here. So the low point in the sinusoidal function is exactly, I think, at 9 months, right? So the sign is the lowest at 9. But the lowest point, the probability of that you get an outbreak, actually occurs before that. So it's because it's how long they're infected, and so it changes all things, depend on all the other parameters in the model. So it gives you a little bit more information and guidance for, when the high seasons are. Okay, so in the last one, I'm going to just talk briefly about 2 other diseases we've been looking at. Lyme disease, and I know I'm a little bit worried about this because I know we have the experts here, but maybe you can give me some feedback. This is a project that we worked on beginning in 2021, when I allowed the students that I was working with to choose their topic. And they chose Lyme disease because they knew about this and they were excited. And so we started working on this, and that was in the summer of 2021. But so I learned a lot, and they learned a lot, and so I'm still learning a lot. Bacterial pathogen is Borrelia burgdorferi, the tick that were we're concentrating Ixodes scapularis. A host is a white-footed mouse, white-tailed deer, humans, etc. What we're doing is what typically done with all the models that we've looked at is that we use the larvae, the nymph, and the adult. We don't use eggs in this case, and we use mice. So we're looking not at the human, but if we know something about the nymph populations, well, then we know the high risk for infections because humans are infected by the nymph. Seasonal variation in ticks, we assume seasonal variations in tick births, deaths, feeding rates are investigated. And so we looked at the literature about the life cycle, because the tick cycle is very complex. It's a 2-year cycle. And so this is what my students drew from looking at the CDC cycle and another cycle proposed by Eisen that we put on here. And so we divided into seasons, but the season I put in quotes here because it's not like what you think of the season. So we're using reference from Eisen and Ogden and also other people, Asfeld and things, but so we're using the stuff in blue here. And so, so in this, the nymph, the unfed nymph activity peaks in May and early July, and looking for a host. Nymph will molt into an adult and gorgeous before August. And so actually the spring here, let's see. Yeah, let me see. Actually, I think starts late. It's like in May 1st, right? So this, they don't correspond, but it corresponds. What we say is, well, this is when these activities occur. So it's a 12-month cycle. But the life cycle of the tick takes 2 years to complete. And so we try to incorporate this in the model through our periodicity and our feeding rates that I'll show in the moment. But we include susceptible and infected larvae, nymphs, and adult ticks. And also we wanted to incorporate the important delays that occur in here. And Zhang Wu and colleague Professor Zhang have a book, fairly recent book that talks about all this co-feeding and behavioral and diapause delays. And we tried to incorporate these in this model. And so what you did, instead of making it a fixed delay and having a delay differential equation, we tried to make it more realistic by putting the distribution to have an Erlang distribution by putting these stages in between where this is our delay. So we have the larvae, which goes through this delay here until it molts to a nymph. Nymph becomes an adult. But in that time, then in order to make the molt, it has to have a blood meal. So it has to feed on mice. And so the mice are in here, but I don't have it in this picture here. The mice are in here. And we experimented with the different types of transmission rates. But here we limited the number of ticks that could be feeding on a mouse. And so we can calculate the R naught in the simple case. Let me go back a second. This is, so it's given like this, and this is the delay, how many stages we put here in the delay. And so okay. Also, there's another assumption in the adults that they do not, that it's not past the infection in the adults does not pass to the eggs. So there's no vertical transmission, there's no transovarial transmission. So they don't pass it on. So we don't have to consider them. So the basic reproduction number here only depends on the larvae and the nymphs and the mouse, right? Basically. So it simplifies a little bit. Let me see if there's anything else. But anyway, yeah, okay. So this is an idealized example, and we've looked at changing some of these things here. So it's fairly complicated. So I think we got overzealous on making these periodic, and so we have so many things here, but tried to make it realistic. And when the feeding rates, this is the birth rate in the spring of the eggs are hatched, and we have the eggs are hatched, and then the larvae, and then they start feeding. Okay, so this is the birth rate. So it's only at this time. And then we have death rates. We have, yes, these look a lot. These in the winter, we have an increase in deaths. This is the adult feeding rate, which occurs in the fall. And then we have nymph from the previous year. Now they're feeding and overwintered, and then the larvae. You know that there's not an overlap of the feeding rate, but we've looked at overlapping too. But here, this simple one, there was no overlapping. So this is an idealized case. Okay. So this is what the endemic solution looks like for their particular parameter values. We also calculate the nymph infection prevalence, the mouse infection prevalence, which is very important for looking at Lyme disease. In this case, the R naught was fairly large, and you can see the large population size in these, but we do get this annual cycles. Okay, but what we're interested in, okay, these are very high. I mean, you know, the NIP, because of, even though, I mean, this is the prevalence, right? So it looks like it's always stays high. That's because even if they're the proportion, we're looking at the proportion of them infected. So it stays fairly high. The mouse, because they have a high turnover there, they have very significantly, the prevalence varies. Okay, so now I'm going to show you what happens when I calculate the probability for those parameter values. Actually, it's 5. Actually, I put 5.1 here. It's 5.06, but anyways, or 5. So we calculate we use that branching process to calculate the from the previous assumptions about the ODE model. The R naught was 5.1, but we calculated this from the branching process approximation of the continuous time Markov chain. This black ones here is if you introduce one infected mouse into that population with an R naught of 5, the probability that it doesn't cause an outbreak is really, really low, because the mouse is it's really low. But if you introduce only one infected nymph, even in that population that has a lot of susceptible individuals, it's not going to persist. You need more than one. You need a lot more. And then suppose we decrease, mouse populations have a lot, vary quite a bit, but we need to reduce those by 20 by a fourth. And so that our R naught was reduced by 2.5. And now these change to the red curves here. The extinction isn't as low because the mouse population is decreasing, the feeding rates are decreasing. This is ongoing research, but now it's obvious that it can't be determined from the R naught, because I tried graphing the R naught. It turns out the R naught is actually 0 for this. If I looked at the R naught of T, if I looked at the instantaneous ones, because the feeding rates do not overlap. So it isn't very realistic at all. So there's lots of stuff we still need to look at that, just to show you. We've also looked at in some other group of our research experiences for undergraduates in 2022, they wanted to look at avian influenza. And so this is the diagram that we used. So the wild ducks in the summer are up in the north. In the winter, they migrate down south, and that's when there's contact between the wild ducks and then the wild ducks down here that contact the domestic poultry or domestic animals, and then humans get infection. So we actually didn't include all 4 of these, but they change during the season because the wild ducks are not introducing it. And so it becomes, here we're using SIR models, and also in order to make it transmissible to humans, there has to be a mutation. Okay, so we included some of these in the model. And we have a migration rate, and this is the migration rate. So 1 is when it's down in it's winter, okay, so it's migrated. And when it's not, we use this function. Also the birth rate for the wild ducks. Wild ducks, the transmission varies between winter and summer. And same thing there's environmental transmission here. Because in the feces, there's virus shed in the environment, so poultry can pick it up too. So we included that, which was done in other ones. Whoops. And it's So I can't say very much about it because we're still working on it, but it's really complicated because there's 4 R nods, there are 4 R values, and it's the maximum of those in the constant case. And we have done a lot of simulations, and we have an preliminary estimate of what the probability of extinction or outbreaks looks like. But it depends primarily on this migration, very much dependent on this migration, because in general, it's the wild ducks that are driving it. So I don't have a clock here, and I hope I didn't go over too much. But in summary, this has been I think the main point I wanted to do is that branching process provide another method for us to look at some of these models, but it is an idealized situation. It's kind of like the null. This is the baseline, and then we can add things to make it more realistic. Connect this, what's very important. It needs to be closely related to data, not only like these simple models here, closely related to data. And there needs to be not only this nice sinusoidal, those can vary. I mean, it has to vary, right? And so that's one thing we've been looking at too. How do you model that by including the variability about these things? And coupling models with data can be useful to public health. And so I'd like to acknowledge all the support that Zhang Wu has given to me and to the program for public health, and incorporating this has been fantastic. And so I thank you. Financial support has been through Texas Tech National Science Foundation. Collaborators on Dengue have been my colleague for a long time at Texas Tech, and a former PhD who has a postdoc now at University of Georgia, Ganesh Fatima Nipa, I call her Nipa. The Lyme disease has been, these are 3 undergraduates that are now in graduate school. It's funny, this Dana, must be, it's Dana Pittman. She's at Texas A&M. We convinced her. She went into, she's going into public health, some applications of public health, but she's studying biostatistics. Johnny is a very good programmer, and this is my PhD student who helped out. And then in the avian influenza, Rowan, they're still undergraduates, but thinking about going to graduate school, that have been working on the avian influenza. So thank you very much. And I'm going to stop sharing. And if it hasn't been too long, I probably lost all my audience. No,
thank you.
If you have any questions.
Linda, you get most audience sometimes as time goes on. And we have Martin. Thank you very much, Linda, for wonderful talk. And this, personally, I like this talk because also those are all the subjects that I really have key interest. We have questions from the audience. Martin, you have a question?
I was wondering, going back to the dengue models,
Yes.
with the tick models, you tried stuff like varying the R0 through manipulating the mouse population dynamics. I was wondering if, or I may have zoned out for a second because I had to respond to an email. I was wondering if with the dengue models, you had tried to draw back those probabilities changing with seasonality to control methods such as insecticide spraying or the kind of lowering of insect recruitment rate, and see how that kind of relates back to those models and perform the sensitivities to guide public health policies, like when to try to get rid of sources.
Yeah, this is a good, so I think that's a really, excuse me, a very good question, I think, to put in the control in there. If we can, now these methods also depend very heavily on the seasonality, that it's repeats. So if you looked at a control that was repetitive, right, I think that we could do that, right? That you're controlling, that you're reducing it at a certain time. What does that effect have? I think that could be done, but you're asking if I did it. No, I did not do it. No, I did not do it. Okay, but I think if as a guideline as to start out, that would be an interesting thing to do it periodic, right? And then we could look at it because it uses this theory. Yeah, so I know I haven't done it, but it's a very good suggestion. Wait, but one thing we did we started to look at, you can also use this for, maybe I'll say that, is this also works if you have one dengue infection and you're looking at whether you have an invasion of a second one, because you can get an invasion reproduction number. This theory also is if you have a stable, periodicity of the first strain, that comes up, you can look at what happens. When is that invasion of the second strain more likely? Right. So that, I mean, it's very similar because you're starting with the, periodicity for the dengue. So, but that's a good question about control. That would be more helpful to, where do you want to go into control? Can we do that and change that high probability of an outbreak to much lower?
Well, it's also the fact that you've got two sources of control. So one would lower the recruitment rate, which is where
Yes.
you're trying to get the pre-adult stages dead, or the
Yes.
other one would be trying to lower the adult population, increase mortality in the adult population.
Yeah. So that one might be maybe, yeah. Yeah, we haven't. So yeah, so it's the recruitment rate, or yeah, so maybe even more explicit dynamics in the mosquito dynamics then, right? Or even if you're talking about ticks, if you're talking about that, right? Look at, we don't have that, yeah, to look at this stage, yeah. And here we're assuming that we haven't varied in the tick one. I don't know if you were mentioning the tick in the mice populations. We didn't vary, they just varied naturally. The infection cycle varied because of the ticks, right? You see the variation though, but if you didn't have the tick cycle, there was very little fluctuations, but they do with the masting cycles. There is a, high change in them. Yeah. Yeah, I mean,
Yes.
yeah. I think we could do some of that.
Thank you, Linda. I saw the Jack Blair thing on the video. So in case you have one question, Jack, you can ask question directly. But I have a question for Linda. So in your dengue slide on dengue, you already show that because that has been bothering me for a while, not only for dengue, but also for for Lyme disease. So for a deterministic model, if you assume the parameter change periodically, you would know if R0 is larger than 1, you're going to stabilize to periodic solutions. And if it's periodically in 365 days or a year, then the periodic solution is going to be that. But in your dengue model, you can see there are two high peaks, and the other things are, so it's not really periodic. How these two large outbreaks took place, which is not explained by the deterministic model. I don't know if the stochastic process will allow us to do that.
Oh, yeah. So what, maybe if I understand correct, this is interesting, if you look at the endemic cycles on this thing, McLennan and Smith, they look at this, you can get, depending on your parameter values, all sorts of interesting things, the endemic equilibrium. You can get chaos, you can get period doubling, you can get all these things. But looking at looking at, when just looking at an outbreak, you're starting at some, actually you could start at any, okay. The disease-free populations, I think the disease-free populations were annual cycles.
Right.
Disease-free, I think it must be the infection or something, I think. Yeah, it's causing these other things to happen when you look at the endemic. But what happens in the CTMC model is the cycles are so high and go so low. The ODE keeps persisting and causing all these things. But that doesn't happen in the CTMC. What happens after these one burst, actually, you saw that I showed you, it actually dies out. Right. So it has to have you have to have something coming in, infection. Otherwise, it dies out because these infections are so big. Anyway, that it dies out. So none of these are persisting. I showed you that even in that, I showed you, okay. Well, we're in the avian influenza, we're looking at these things and we see this, this cycling and nice cycling. But what we see in that, when we do the CTMC, we see a high peak and then that's it. It was very seldom persists. Right. So it's not closed.
Yeah, it's a periodic, but it's not in the same period as you.
Yeah. Yeah.
That's right. Yeah, so you have this in between endemic time period, which is not really so the solution is not is periodic, but it's not periodic with the minimal period we're talking about. Thank you, Linda. I have a Demei Cheng. I believe this is a spatial geographer from Queen's University. Demei.
Yeah, okay, sorry. Let me see. Okay, sorry about it. Okay, hi.
Hi.
Yeah, I'm not in mathematicians. Okay, to be honest, have very little knowledge about those kind of formula you've been talking about. My work actually is more on geographer like variations perspective of the infect disease. We do like using mathematical models, try to understand how their spatial variation occurred and what caused them. I think one thing is really bothers me actually. It is the seasonal variabilities, and but I look at your like slides about like how you incorporate the time into the mathematic like the formula, whether it's deterministic model or stochastic model. One thing I kind of quite not understand is like in your time, like when you incorporate time, I saw you use the functions, right? It's you have a pyramidal like with a different season. But in the realities, if you go to the to check, and those kind of the different, for example, how the life, the timing, and of mosquito, for example, the population grows. They impacted not just the seasonality, but also other like the environmental factors. Actually, is also time dependent, right? For example, precipitations, for example, the moisture levels, right? And so, but those, it's not kind of, you cannot use like a fixed like functions to kind of model that, right? Because they have irregularity in they can change year by year, right? And season by even day by day, right? And they can also, I think, impacted by, for example, moisture. And you may say, oh, I can take moisture as a function of the precipitation, but it also moisture can also be impacted by, for example, the land use, right? And the soil type, right? And so all of those actually impact the seasonalities and the variations. So how we're going to incorporate those also into the seasonality through whatever the models. So I just want to know, like, what's your thought about that?
Oh yeah, like this is really hard. Yeah, this is the key, right? The data. How do you do this, right? And so we've done it through like the transmission, the first one, or the recruitment, right? I mean, this is very simple. But even that, I think this, because these are nice period. Nothing is like that, right?
Yeah, yeah.
So this is like this is the baseline, right?
Yeah.
So okay, so so this is what the problem. One thing we started fitting temperature data, right?
Yeah.
We looked at some temperature data because we looked at temperature data. And so one thing that you can look at, although it's changing now, but we looked, it does have a seasonality to it. So you can fit the mean.
Yeah.
Okay. Yeah. And so then you have to have along that mean, you have to have the variability about that mean.
Yeah. Yeah.
Now we can do that with the stochastic differential equation by assuming some. And there's some nice new stochastic ones that are called mean reverting processes, that the mean now is a period. So mean is a periodic function. And that's the mean like of the temperature. But then you can incorporate, like if you look at the data and you look at how much it varies, you can fit an approximate distribution of how much that goes beyond that. And now each year it looks a little bit different. So putting that in there would see how much that changes, even these simple ones that we put, like maybe the recruitment. But you're right. We also have environmental variability, that decay. You have virus in the environment. For us, the avian influenza, it does persist in the environment for a period of time when the temperature is not too warm. So the temperature does affect it, but probably it's the ground temperature that's important.
Yeah.
So you got to measure the right things, right? and it depends on the locality, right? I mean, the poultry are probably maybe in a place where if they're in house or something, or in, it's all depends. But I think you can incorporate, but now maybe the question you're asking, how do you incorporate that to this model then, right? For transmission and migration is easy, right? They come down at this time, right? And they go back up. So you have this contact, but actually where the transmission is important, and it's the temperature that depends. That temperature is probably that, but I don't know, unless the temperature is the causing, it's hard. It's a hard question. I think maybe probably John Wu has also thought about this a lot. Because I know you fit these, temperature, and you put maybe humidity, relative humidity is also important. They say like for influenza and things. So this is the hard. So that's what we need to talk to people about. Where would we put this? And it's not isn't, I even talked to people looking at mice. I have a colleague that's a mammologist, and it took 2 years after the dry season. You got 2 years after you had moisture, right? Then the grass grows, then they have resources until you see the explosion of the mice populations. So we could say, okay, well, there's a delay. We know it's here, and then it's a delay, and then that happens. And so if we can model it that. So there's all sorts of things that, this is assuming that it's very simple, but it's actually, so this is this. And then what happens? So next question is, what happens if you put the true variability about this and then connect it to the model is the big
Yes,
the big question.
Yeah, I think one thing is, even just the temperature itself, I found it could cause some kind of probably dramatic changes in the model output. For example, what kind of temperature we use, right? Let's say usually we do our average, the means, right? But in the realities, you see the temperature can change a lot. Just look at how the last couple of days, how our temperature goes from minus, the 20 something, and then to now above the 0. And then you see how those will impact for mosquito, for the larva, how the death rate. They could just change in just a couple of days, right? And then they suddenly change it. But in our model, I think we don't reflect that, right? You use the mean, and you will never be able to catch those kind of the real, the extreme, the event. So this is something I have been thinking about. Said about how we could kind of incorporate the time, continuous, the changes, time difference, and temperature difference. How the suddenly, during the real change in the temperature, not just the means, monthly means or daily means, and how those could improve our prediction accuracies. Well, that's just I know it's.
But I guess you have to know too. When this gets really low, the temperature gets really low, freezing, right? That then this is a threshold where that you have a certain mortality, right?
Yeah.
But I think you can incorporate some of the temperature data that does go fluctuate high by adding to this mean some function or even a distribution that goes above and below with some kind of model, right? But you fit the mean, right? You have this, and then it always goes back to this mean, right? But then it can fluctuate, because I think that's true. It's extremes in here. We have long periods of drought, which affects the wildlife a lot.
Yeah.
Everything. And so that's very, very important here. And it's not just, so. Right. Yeah, I think that's important. I think it's really important. Yeah.
Okay, thank you very much. Yeah.
Thank you.
Thank you for your question.
And we should organize a physical meeting to have long.
To do this. This would be very interesting. I think so.
Yeah, thank you very much again, Linda. Thank you all for attending in today. And we are looking for some opportunities really to bring Linda back to Toronto and have longer, more time for discussions and zoonotic disease is really in our top agenda for the Mathematical Public Health Network. So
people have expertise in other things would be really interesting and fun to collaborate. Thank you so much. Thank you so